Hi guys, in this video we're going to talk about the expected value of discrete random variables. So far all we've talked about are discrete random variables. And the example in the last video we had omega was the space of outcomes if we flip a coin 3 times. So remember that H represents 3 heads, or T represents a tails in the first flip, heads in the second, and a tails in the third flip. And then we had a random variable x, which just counted the number of heads that we flipped. And so one might ask, what's the average number of heads that we expect to see if we do something like this? Or what's the expected number? So the expected value, this is a definition of a random variable, x, is denoted by, so we use e, and it's like a function of x. So we plug in x, and this gives you out a number. So the expected value of x is just going to be the sum, or we'll call it I, times the probability that x equals I. So you just add up all the numbers, I times the probability that x actually is equal to I. And so you only care about values that x takes with a positive probability. If x doesn't take value I, then the probability of this is 0, and so you're just adding in zeros otherwise. So that's the definition in general of an expected value. So let's use that to compute the expected value of x in this example. Okay, so the expected value of x in our coin flips example, we can get 3 heads. So here we'll use I equals 3. 3 heads times the probability that x equals 3, plus 2 heads times the probability that x equals 2, plus 1 times the probability x equals 1. And then you could add 0 times the probability x equals 0, but 0 times anything is just 0, so there's no point in adding 0 to this, and we'll change the value. And now this is equal to 3 times, and what's the probability we get 3 heads? Well, 3 heads has probability 1 over 8. And then 2 times the probability that we get 2 heads. So there's 1, 2, 3 ways to have 2 heads. So it's 2 times 3 over 8, plus 1 times, and then the probability we have 1 head. Well, there's 1, 2, 3 ways to have 1 head. So 3 over 8 chance that we have 1 head. And then if we just add this up, we have 3 eighths plus 6 eighths plus 3 eighths is equal to 12 over 8, or 3 halves, which is 1.5. So if we flip a coin 3 times, the expected number of heads is 1.5. So note that the name expected value is a little misleading sometimes. We don't actually expect to have 1.5 heads, because you can't possibly get 1.5 heads if you flip a coin 3 times. But it just means the average value. So on average, you're going to get 1.5 heads. So let's take another example to show that whenever we're talking about discrete random variables, anyway, then the expected value really is the average value. So a place you guys are probably used to having to take averages is when you're computing your own grades. Suppose you get the following scores in a class. So here's your class scores. Maybe you get a 60, an 80, an 80, a 90, and a 95. And now you want to figure out what is your average in the class. So how do you do this? Well, you just add up all the scores. 60 plus 80 plus 80 plus 90 plus 95, and then you just divide by the number of scores that there are, so you divide by 5. Okay, but if the scores are evenly weighted, we could let x be the random variable that denotes the scores. So your scores aren't completely random, but if we treat them as if they were random, so you could let x represent the scores, then we would have the expected value of x is equal to, and we can compute it using that formula that I just showed you. So There's 5 values here. So the probability that x equals 60, so we can say 60 times the probability x equals 60 plus 80 times the probability x equals 80 plus 90 times the probability x equals 90 plus 95 times the probability x is 95. And now the probability that x is 60 is 1 out of 5. Right? There's a 1 out of 5 chance that you would choose 60 if you choose one at random. 80, well, there's 2 out of 5 chance that we get 80. And then a 1 out of 5 chance we have 90. And a 1 out of 5 chance we get 95. So we've got a common denominator here. Let's just put all of this under the same denominator. This is 60 plus 80 times 2 plus 90 plus 95 all over 5. And what does 80 times 2 mean? If we think back to elementary school, that just means 80 plus 80. Right? That's what 80 times 2 really means. So this is 60 plus 80 plus 80 plus 90 plus 95 over 5, which is the same formula you use for your average formula. So it really is just computing an average. But why would we do it this way instead of doing it this way? Well, let's change the example just slightly. Suppose these were your scores, but these two scores are in exams. So you scored an 80% and a 90%, but these are worth 50 points. And then on these 3 scores, these are some quizzes or something, and so these are worth, I don't know, 20 points each. So you got 60%, 80%, or 95% out of the 20 possible points. Well, whenever you go to compute your average, you can't just do 60 plus 80 plus 80 plus 90 plus 95 and divide by 5. Right? These are worth more points. So let's talk about a slight variation of how you compute expectations. Well, we might do that example in class, just so we go ahead and compute it out. But you should maybe try beforehand and see if you can do it before we get into class. So remember that x is a random variable. It just means that x maps from omega to the real numbers. But you guys are familiar with functions, regular functions, and from algebra and calculus and all that. It just goes from r to r. So an example of this may be like f of x equals x squared plus 1 or something. Okay, that's a function from r to r. But now we can compose the two functions. So composition of functions f of x would be a map from omega to r. So if we compose a function from r to itself with a random variable, we get a new random variable. So f of x, or usually we write it f of x this way, is also a random variable. So maybe we could refer back to a coin flip example, but let me do fewer flips so it's a little shorter to write. So say we flip a coin twice. And x is the number of heads. Okay, so now then we can compute f of x. So remember that, so x of heads tails would equal 1, but f of x of heads tails would be f of 1, which is 1 squared plus 1, which equals 2. So we could ask, for example, what's the probability that f of x equals 2? And it's going to be So what does f map to 2? It's going to be the probability that x belongs to the set 1 and negative 1. Right, because f of 1 equals 2 and f of negative 1 equals 2. But those are the only 2 points. And so now we have the probability that x belongs to this set, and this is equal to the probability of the set heads, tails, and tails, heads. Right, which is equal to 1/2. Okay, so we can apply any kind of function to a random variable to get this new random variable, and we compute with it just the same way. Although we might have to take extra inverse functions or something to compute the probabilities. But now we want to compute the expected value of a function of a random variable. So what is the expected value of f of x? So remember that the expected value of x is equal to the sum, you just add I times the probability that x is I. Well, here we're going to sum over whenever x is I. We're still looking at x as the random part, right? F just goes from R to R. So it's the probability that x is I. But if x equals I, then you have to plug it in, and instead of getting I, you get f of I. So this is the expected value of a function of a random variable. It's the sum over f of I times the probability that x was I. So if we wanted to compute the expected value of f of x in our previous example, so x is number of heads and 2 coin flips. And we just said f of x was x squared plus 1. Then the expected value of f of x, here this is the random variable x, not the little x. This is equal to, so what could we get? We could get, x could have 0 heads, which would make f of x 1. So it would be 0 squared plus 1 times the probability that x equals 1. 0. Plus 1 squared plus 1 times the probability that x equals 1, plus 2 squared plus 1 times the probability that x equals 2. So note that we just plug in the value of a random variable for this little x into this formula. And so this is 1 times the probability that x is 0 is going to be 1/4, that's 2 tails, plus 2 times the probability that x equals 1, which is 1/2, because that would be a heads and a tails or a tails and a heads, and then plus 5 times 1/4, which is the probability that we get 2 heads. Right, and so now then this is equal to, we can get a common denominator. We have 1 plus, so we want to multiply this by 2 over 2, so we have 4 plus 5 divided by 4, which is equal to 10 over 4, which is 2.5. So if you were to play some gambling game, and they told you, well, we're going to flip a coin twice, and however many heads that we get, we'll take that and square it, and then add 1 to it, and that's going to be your payoff in the game. Then the average amount you're going to get during a game is going to be 2.5. That's the expected value of your payoff for a given game. And if you guys remember, we talked about before, well, this would be assumed to be the fair price of the game. So if you were going to be charged for this, $2.50 would be the fair price to charge. All right. God bless you guys, and I'll see you soon.